I've heard many talks from Alessandra. I've always found them so enlightening and inspiring. I just learned that she got her PhD in Pisa and then was at Caltech as a postdoc, but in between stopping to work with Thibaut Damour, who the theorists here will know. Yes, yes, indeed, it was predicted. Massimo, let me introduce Alessandra Buonanno. Where so Thibaut Damour is a very eminent theoretical physicist, and she got interested in gravity things there and went to Caltech. It was the days that gravitational wave experiments were really coming on mass show, one might say, in terms of really being feasible and so on. Anyway, by now, he's the director of the Einstein Institute and the Max Planck Society in Potsdam. And continues amazingly to do fundamental work in theoretical gravity, I would say, correct me if I'm not right, and is doing a leadership role in these international collaborations like the LIGO-Virgo collaboration and future collaborations like the Cosmic Explorer and the Einstein Telescope. Anyhow, it's really lovely to have you with us. She's going to be here the rest of the week and Monday, and hopefully we'll make such a good impression on her that she comes back.
Okay. So first of all, I want to thank people here for inviting me. So it's my first time visiting NYU, and I'm having a great time. So let me then start. So first of all, I want to show you this plot that maybe some of you have already seen, I'm pretty sure. It's a collection of the binary black holes that LIGO and Virgo have discovered in the last 10 years, and also neutron stars. The y-axis here is the mass of the objects in solar masses. And the way of reading this plot, you have one black hole, another black hole in a binary, they merge with each other, they form a new black hole that is here. And I want to highlight a couple of events. The very first discovery, 10 years ago, the 14th of September 2015, this is a still picture of a numerical simulation that was done at the time. An event is here. The first binary neutron star that was discovered the 17th of August 2017, which is here. The neutron stars are in orange in this plot here. The first, at the moment, the largest actually binary black hole observed today, with black holes of masses 90 and 60 times the mass of the sun. The most asymmetric binary discovered with a mass ratio around 10, which is also a puzzling source, as we will see later. And I want also to highlight that besides these 100 coalescents discovered and published, the LIGO and Virgo collaboration has gone through a run, the most recent one, called the fourth observing run. And as today has discovered 203 signal candidates. We call them signal candidates and not gravitational wave events, because these are just the events that are publicly, announced for looking at electromagnetic counterpart, but papers are under, we are writing papers, so they will come out in the next months. And the only event that has been published until now from this run was discovered the 29th of May, 2023, soon after the run started. And it's an interesting neutron star black hole system where the black hole has a small mass. I will come back to this later. In this plot, you see in red the black holes that we see in our galaxy as part of binary system, and we observe them as X-ray sources, like the very old Cygnus X1, the very first discovered. And in yellow in this plot, you see the neutron star in our binaries that have been discovered as pulsars. Okay, in this talk, I want to describe the theoretical framework that has underpinned these observations. I will describe how we develop the waveform models to detect the signals and also to extract information from them. And I will do that also highlighting some of the results in astrophysics and also fundamental physics. And I will then turn of what are the theoretical challenges for the future, because we will have detectors that are going to be more sensitive than what we have today on the ground and in space. And if we don't want to have an incorrect scientific conclusion in the interpretation, we actually have to improve the waveform models that we use today. But now let me go back to the origin. So gravitational waves are a signature of the dynamical space-time. They were predicted by Einstein in two papers. The very first one in 1916, where he started from the Einstein equation that I wrote here. This is describe the curvature of the space-time. R mu nu and R depend non-linearly on the metric and its derivatives. And here you have the energy momentum tensor. He linearized this equation, writing the metric like some flat space-time metric or Minkowski plus a perturbation. And in a particular gauge, you arrive to this equation of propagation of the waves. This is the D'Alembert operator. And this resembles an equation that I'm sure everybody here knows in electromagnetism. If you were replacing T mu nu with J mu, the metric, the current, and the H bar mu nu with A mu, okay? You get a similar equation. Of course, the complication happens when you start adding corrections in H mu nu in this equation here, which I'm not going to describe in this slide. Einstein actually made a mistake in the first paper. In deriving the degrees of freedom, the radiative degrees of freedom associated to the gravitational waves, which today we call the plus and cross polarization, he made an algebraic mistake, which he corrected in a paper in 1918, where importantly, he derived an equation that describes the energy flux of gravitational waves. He also made a mistake of a factor 2 that was corrected by Eddington, actually in Cambridge at the time. And this equation shows the energy flux as a function of derivative of the quadrupole moment. And in fact, in this paper, he realized that the gravitational waves, the possible source of gravitational waves, are like a rotating dumbbell, like a binary star system. Of course, at the time, he didn't believe that there were binary stars in the universe. He also thought that the gravitational waves are very weak. We might not be able to detect ever them. But of course, today we know that this is actually possible. So another important result I want to highlight at the beginning of my talk is that in describing the dynamics of two black holes going around each other, we rely very much on the analytic solution for a black hole in the non-rotating case, which is the Schwarzschild solution derived by Schwarzschild in 1916. And after 48 years, the solution derived by Roy Kerr for a rotating black hole. In fact, up to now, all the observation says that these are the black holes that we are seeing within, of course, the statistical error that we have from the observations. And there are also other ways in which people have proved that astrophysical black hole seems to be, the Kerr solution. Now, we are interested in binary systems. So you can have a small black hole that go around a large black hole, like in this plot here, where the black hole is represented by a funnel. You have a small black hole going around a big black hole. And you can describe this motion using the solution of Kerr or Schwarzschild. But quite interestingly also, by learning the solution in this simplified case of a small body going around a large body, you can actually learn also and inform the solution when the two bodies have comparable masses. This may appear a bit strange, right? Because when you have two black holes that merge with each other with comparable mass, the dynamical space-time is changing very abruptly. While if you have a small body going around a large body, it's much more simpler, the situation. You have just a perturbed space-time or Schwarzschild or Kerr. But actually, it turns out that if you use mappings that include the mass ratio in the binary, you can inform the body dynamics for comparable mass just using this simple case, as we will see later. Okay, so let me tell you some numbers now. What is the strength of the gravitational waves? And I'm going to focus just on binary systems because these are the systems we have seen until now and are the ones that are, of course, more familiar with. So in a binary system, you can introduce the mass. You go in the center of mass, so you have the reduced mass. And you can also introduce a parameter, which is the reduced mass divided by the total mass, which varies between 1/4 when the two masses are equal and 0 when one body is much larger than the other. And you can also work out what is the quadrupole moment of this system. Well, from Einstein, we know that the strain, this is just, I dropped the indices, okay? It's a tensor, but I'm just dropping the indices. is proportional to the variation in time of the quadrupole moment of the system, differently from electromagnetism, where you have the dipole, okay? You have variation in the dipole. In gravity, it's the quadrupole, and the d in this equation is just the distance of the source from the Earth. Now, you can compute the quadrupole for a binary system, and you find that it's basically proportional to the velocity square. Okay, if you compute the quadrupole, you take two derivatives, you get something proportional to the velocity square divided by the speed of light. And now, if you assume the two bodies are moving on a circular orbit, you can actually trade this velocity with the angular, basically, velocity of the binary system. Just using the Kepler law, you can relate V to basically R, the separation, and omega. Now, if you put some numbers for a neutron star in the Virgo cluster, which is the closer cluster to us with 3,000 galaxies, you get a very tiny number. But if you were computing the radiation, the luminosity, the energy per second, you get actually still taking one derivative of h and squaring it, the same way in electromagnetism, you obtain something which is proportional to V divided by the speed of light to the power 10. And C to the 5 divided by G, it's an energy per second. It's an enormous energy. And notice here this power here, because this tells you that unless you have objects that go almost at the speed of light, you will reduce the luminosity by a lot. And you need objects that do not distract. They are not distracted as you bring them close to each other at the speed of light. And that's why you need black holes and neutron stars. Normal stars, you cannot do that. They will be distracted if you try to bring them very close to each other. Also, they will touch each other actually very soon. Now, this energy, it's very large. It's similar or larger than the one in the all visible universe, although it's emitted only at the very end, okay, before the two objects merge with each other. And I also wanted to emphasize that once the waves are produced, they travel up to us, and they are not much contaminated or deformed by whatever they encounter. Although at the end of my talk, I will show you that actually we have to start caring about phenomena like gravitational lensing that can have an imprint on the gravitational waves, like it does in electromagnetic astronomy. Okay, so in order to detect the waves, so there are interferometers that have been built. These are images of LIGO and Virgo. And the key idea is how the waves interact with free-falling body. For example, this ring of particles, as the gravitational wave impinges on the screen, is squeezed and stretched. And the free-falling bodies are the mirrors that hang by wire at the extremity of a Fabry-Perot cavity in the interferometer. Of course, they are not completely free. You know, they are pendular, and they just are free of moving above a few hertz. And what is monitored is the displacement or the variation in the proper distance between the mirrors, looking at the shift in the light that is imparted, and this variation is proportional to the strain. And so if you want to detect something of this order of magnitude, as I was saying before, you need to monitor displacement of the mirrors of this amount, very tiny amount. Now, another important thing to keep in mind is that for binary systems, we have the luxury that we can know in advance the shape of the waveform by solving the Einstein equation, as we will see. And so the best tool to actually detect the waveform is to use signal processing or match filtering. And I have here a small animation. So on the bottom, you have the data in black with maybe a signal. You correlate the data with a template, which here is represented in pink. You maximize the correlation on the parameters of the binary, for example, the masses or the spins, if the black hole carries spin. And if the correlation becomes larger than a certain threshold that you have fixed based on the knowledge of the noise in your detector, basically false alarms, you know, that you can basically produce sometimes this kind of fluctuation, this kind of events just from a random fluctuation in the noise. You can claim a detection. Of course, you also do coincidence between detectors in order to get rid of false events. And so you need a template bank, and you need 100,000 of templates in these template banks. a million of templates are generated when you do the follow-up analysis using Bayesian analysis to extract the parameters. So now let me go back to the formula I was giving you before, where I was mainly mentioning the amplitude, okay, of the waveform. But now what is important is also the phase, because in match filtering, what counts is actually the phase of the waveform that you have to predict very accurately. And I want to say how actually we determine that phase, first in a very simple way. So in order to determine the phase, which by the way, in this formula, there is a factor, so this phi t is the orbital phase in the binary. And the reason why there is a factor 2 is just the quadruple formula. If you had a dipole emission, there will be 1 instead of 2. Okay, there. So how do we get this phase? Okay, you can basically use 2 ingredients. Once the binding energy, one of them is the binding energy of the system, which I wrote here, just the leading order term, just using Newtonian gravity. And basically, in Newtonian gravity, you have the kinetic energy, you can relate to the potential through the Bayes theorem, right? And so the leading order term is this one, but then you can have corrections that depends on V, okay, higher order in V. The other ingredient is the luminosity, is the flux at infinity. Okay, the formula that was derived originally by Einstein, although not for binary systems. And then what you do is that you put them together. You say, okay, there is an energy balance equation. The variation in the binding energy has to be equal to the flux at infinity. Okay? And for quasi-circular orbits, again, everything depends only on this orbital frequency omega. So you can rewrite this equation as dE over d omega over dt. So you have omega dot expressed in terms of this, and then you just take integration and you get the phase. So you need 2 ingredients to get the phase, the binding energy of the system and the dissipation, the luminosity. But you cannot just use the leading order terms. You will get an answer, but it's not very accurate, okay? You cannot just use Newtonian gravity to describe the dynamics because of all these relativistic corrections that are very, very important as the 2 bodies merge, are very close to each other, where V over C can be really very close to 1. Okay, so now I want to also make another point. So this animation here represents 5 of the binary black hole detected by LIGO and Virgo. And here you have the binary neutron star, which is very long, okay? The bandwidth of the detector, LIGO and Virgo, is between 20 Hz and 1 kHz. And some of these signals are very long, some are very short. Why that? Well, the gravitational wave frequency is a multiple of the orbital frequency, okay? The frequency is increasing as a function of time. At some point, the 2 objects just merge with each other. And when that happens, as a rule of thumb, you can determine it like something of the order of 4,000 Hz divided by the total mass of the binary. So a binary neutron star has a mass around 3 solar masses because the neutron star are around 1.4 solar masses. So the merger is in the kilohertz. And that's why this signal is very, very long. But black holes are much more massive. The one that we are seeing are 30, 40, 100 solar masses. And so they merge in the 100 of Hertz. And that's why the signal is much shorter because they start sweeping in band around 20 Hertz and then they just merge. And notice if you want to look at million solar mass black holes, you have a merger frequency around the millihertz. So you have to go in space to see them. You cannot see on the Earth because there is seismic noise at much smaller frequency, so you cannot see the system, as we will see later. Now, besides detecting the signal, we are interested in extracting the parameter. That's why we need to know the phase very well. How do we do it? How the parameters are printed on the waveform. So from the frequency evolution, the way in which the frequency evolves over time, you can extract the masses. If we know the amplitude and the masses, we can reconstruct the distance. This was also in my previous equation where I was showing you the amplitude and how it depends on the distance and the mass. If you determine all that, you can get the distance. If you know the time of arrival, the amplitude and the phase at the detectors, we have at least 3 detectors operating, Virgo and the 2 LIGOs. You can reconstruct the location in the sky, where it happens, where the event happens. Now, this signal here is for 2 black holes going around on a circular orbit, not even spinning, so the black holes are not spinning. This signal is slightly more complicated because it has modulation that are induced either from the precession of the spin of the black holes, or the orbit that is not circular but is eccentric. And by determining them, you can extract information on these parameters. You can also build a waveform not in general relativity, but in some alternative theory of GR. This is something that is happening in the last years. And when you compare with the data, you can extract information on a gravity theory, which is not general relativity. And we'll see some examples later of this test of general relativity. Okay, so the most important thing here is to compute this waveform with high accuracy. And you have to solve the Einstein equations. And this is much more complicated than solving the problem in Newtonian gravity, where it's very beautiful. In Newtonian gravity, you have an equation that in closed form that describe the orbit. Okay, this is what we learn in high school and classical mechanics course, I guess. But in general relativity, it's more complicated. You don't have a closed form expression of the orbit because of the non-linearities. And moreover, the orbit, as you know from the precession of Mercury, is actually not fixed in space. It rotates like a rosette, okay? Like you see here in this plot. Actually, this is one of the stars going around Sagittarius, a star. Is taken from the Max Planck for extraterrestrial physics. And for us, not only you have a very quick, actually, precession, because the objects are very relativistic, but also the ellipse also shrinks in time, no? Because the two objects come closer and closer to each other.
Alessandra, this
Yes.
is illustrative. This is not real. This is not a real orbit.
Actually, this one is the real orbit of S2.
No, but the rotation due to the relativistic precession is exaggerated completely.
Yes.
Not...
I agree with you. But the one of the binary black hole we are observing is very larger than than what you see here. So what I was saying is that you cannot have an analytical model closed form for the orbit, but you can have an approximate solution. So then what we do is that we solve this equation on supercomputers, and then we solve this equation in an approximate way, as you will see in a moment, and we put together these two approaches, and we build waveform by combining numerical and analytical relativity. Now, why we cannot just rely on supercomputers? Well, because it's very time-consuming to produce these simulations. If you want to do just 15, 20 orbits of two black holes going around each other, it can take 1 month, but even 6 months, depending on the mass ratio in the binary, depending on the speeds. So you cannot solve this problem and produce 100,000 or million of simulation or waveform that you need for detection and follow-up just using supercomputers. I'm showing you here a simulation that represents two black holes of equal masses. This is the flux of radiation, and this is the waveform, the two polarization, just in the last hundreds of milliseconds. And the radiation is emitted everywhere. This is when the two black holes merge with each other, but is in particular emitted along the direction perpendicular to the orbital plane. And in this particular case, the orbital plane is not moving because there are no spins. Okay, so how do we actually solve this problem at a high level? So on one side, we can solve this equation numerically, as I was saying before. So I introduce this cube here. This cube represents the binary parameter space, the mass ratio in the binary, the separation, the eccentricity. So you go from bound orbit to scattering. And depending on the region in which you are, there are some analytical methods that are more suitable than others. And of course, there is also numerical relativity, but as I said, numerical relativity is only restricted to a certain region of the parameter space. So the oldest method is post-Newtonian theory, where you solve the Einstein equations in powers of V over C square, V square over C square, or GM over RC square, because of the Weyl theorem. And this is suitable when the two bodies are very far from each other. You can expand the Einstein equation in powers of G or Gm over RC square without expanding in the velocity. And this is called post-Minkowskian approximation. It has had quite a lot of attention in the last few years, and we'll come back to this later, because it brought people from actually working in scattering amplitude and effective field theory to work on this problem, classical VR problem. And finally, you have gravitational self-force. So if the mass ratio in the binary is very large, so one body is much larger or much smaller than the other, then you can expand the Einstein equation in powers of the mass ratio. And this approximation is in the strong field. You don't do any expansion in the velocity. That is limited to systems where you have a small body going around a large body. Now, this is not enough. You have to put together these approaches. One way of doing it is using the effective one-body approach, formalism, that can resum, include this information, but in a resum form, and also as a physical ansatz for the merging down, that then can be made more accurate using numerical relativity. Now, sometimes you will see in some of the plots later on some names like SU-BNR, spinning, effective one-body numerical relativity, or this other name. So these are just names of these models, okay? Don't worry too much about that. There is another way in which you can build the waveform. I mean, the previous one are built in the time domain by solving the Hamilton equation with the radiation reaction force. You can build frequency domain waveform phenomenologically by putting together the effective one-body, post-Newtonian numerical relativity. And this has been also very successful. You basically build a closed form expression in frequency domain. And this is just a representation of the waveform, the amplitude and derivative of the phase, just to show you during the spiral merging down that they can be quite simple expression that you can actually build in closed form in frequency domain. So this is very easy to generate because they are in frequency domain, but they are less accurate than the previous one, just because you make some approximation in order to produce them in closed form. Finally, today, in the last 5-6 years, people have also developed waveforms that are called numerical relativity surrogate, where in the region in which we have numerical relativity, you basically interpolate directly the numerical relativity waveform. And so this is our most accurate waveform, but they are limited in the region in which numerical relativity is available. And here I'm just showing you the comparison of one of these numerical relativity surrogate model with numerical relativity. So you can see the good agreement compared to an effective one-body waveform, which was not actually calibrated or tuned to numerical relativity for this part of the parameter space where you see more differences. Okay, so another important thing is that until now, all the waveforms that have been produced are just for black holes or neutron star, let's say in vacuum. So there is no, for example, effect of gas or the fact that the bodies can be, for example, in the case of a small body going around a large body in an accretion disk. But in the last few years, there has been a lot of interest in starting to include these effects that are called environmental effects, which here are represented just putting some green around the black holes, including, black hole that could be moving some medium, but also starting to include effect beyond general relativity. And if you do calculation in effective field theory, where you do Feynman, diagram representation of the events, for example, this is for the scattering process, you have to introduce, for example, some new operators. If you have a scalar tensor theory, you will have also some scalar fields that you have to take into account in order to produce, the waveform in these beyond GR theories. And this is work that actually has become also quite active in the last few years, including numerical relativity simulations in beyond general relativity. So I have one slide just to explain to you how we actually built this model that are calibrated to numerical relativity, starting from the analytical ones. So I make an example in the case of the effective one body. So you start with a model which is not calibrated to numerical relativity in red, and you compare with numerical relativity, you see that there is a dephasing as the two bodies go toward merger. And then you reduce the dephasing until they agree very well with each other by extracting some information from numerical relativity and injecting the information in the analytical computations. And now this is done for one numerical relativity waveform. You repeat this process for many numerical relativity waveform in the parameter space, for example, of the mass ratio and some combination of the spins in the binary. So the different colors correspond to different mass ratios. And you repeat this process in all the points in which you have numerical relativity, and then you extrapolate outside that region. I mean, I'm not going to explain to you how we do that, but at the end, you have to produce a model that you have to basically evaluate for any mass ratio and any spin. for the template bank, for example, of LIGO and Virgo. So this is actually a projection of the template bank in the mass plane, mass 1 and mass 2. So for binary neutron star at low masses, post-Newtonian templates are used, 75,000 of them. For neutron star black hole and binary black holes, so we need to include the merger also, and that's the way in which we tune these models with numerical relativity, so that at the end we think to have a model that is quite accurate. Okay? Of course, this is just limited also to the number of numerical relativity waveforms that we have. Okay, and there are also, here I was highlighting actually the model that we have developed for the current run, which is going on in this family, which is called SUBNR, but there are also other models that are used for follow-up analysis. So let me give you some highlights. I can only describe the events of the previous run, because the one of the ongoing run under analysis, I cannot talk about them, except for one of them, you will see later. So this event was discovered the 14th of August 2019. It's a peculiar binary because the smaller object has a mass which is between the mass is too large to be the mass of a neutron star, given the equation of state of the neutron star that we know today, but perhaps too small to be the one of a black hole formed by a collapse of a star. So we don't know yet. But this event was also interesting because of the large mass ratio in the binary, around 10. Now, the more complexity and some structure you have in a binary, for example, the asymmetry due to masses or to spin, the more harmonics are actually emitted. So I was telling you before, the quadrupole is the leading order emission of gravitational waves, but then you have higher harmonics. And in this simulation here of the events, you see the total signal, then decompose in harmonics. This is the 2-2, the quadrupole, the 3-3, the 4-4. And these harmonics become more and more important as the two bodies approach each other, because the amplitude of these higher harmonics scale with the velocity divided by the speed of light. But now in the models, when you include the presence of the higher harmonics, and also the precession of the spins, the P and the HM in this plot, and you look at the reconstruction of the mass of the secondary, which has this puzzle value, you can get a very tight posterior with an error around 10%. If you didn't include these effects, higher harmonics and precession of the spin, you will have much broader posterior distribution. So these physical effects do matter in extracting the parameters. The other example I wanted to make is the very large binary black hole that I mentioned at the beginning of the presentation. This is a numerical simulation that we did in our department. And you see here the two black holes merging with each other. It was a very short event because of the large masses. So it merged almost immediately after entering the bandwidth of the detector. And this is posing some challenges, this value of the masses, because from theoretical astrophysics, we are told that we should not see black holes that come from the collapse of stars with a mass between 40, 50 solar masses up to 120. And so where these black holes come from? Well, maybe they come from a previous merger of two black holes that then form a black hole, and the black hole, merged and ended up being captured by another black hole, and that formed a binary. Of course, some of you may be excited that this could be primordial black holes, okay? But we cannot really discriminate between them. So I wanted also to show you the parameters of this binary reconstructed with the waveform models. There are three of them here, including the null surrogate, and these are the masses of the event, and these are the spin parameters, the spin along the direction perpendicular to the orbital plane and on the orbital plane. So Chi-P tells us information about the precession of the event, and this is the prior. So the fact that you see these posteriors different from the priors tells you that maybe there is some hint of the precession of the spin for this event. But the reason why I wanted to show you this event is also because you see more differences between the waveform models. It's still okay, we are not dominated by systematics, but as the signal to noise ratio is going to improve, the statistical errors is going to become smaller, right? If you don't improve the waveforms, you're going to be dominated by systematics, okay? And you will see more examples later. So now I want to tell you something about the neutron stars. So the neutron stars are very interesting also to see in gravitational waves, because these objects, we don't know yet what they are made of, in particular in the inner core, the so-called equational state of the neutron stars. And we can shed light on that because the neutron star has a parameter which is not there for black holes, which is called the tidal deformability parameter, or the lab number. And this is basically given by the quadruple moment of the neutron star that is acquired because of the external tidal field of the companion, a kind of tidal effect. And how we can measure it? Well, if you take a binary black hole waveform and a binary neutron star waveform with the same masses, they are similar to each other at very large separation, but as the two objects come closer and closer to each other, they have a difference. And this difference is due to the presence of this lambda parameter for the neutron star. So you see also very large difference at merger between the neutron star and the black hole. But even before arriving to merger, you can have a dephasing. Unfortunately, the merger is in the kilohertz. I was telling you this at the beginning. And at the kilohertz, we don't have a very good sensitivity of the detectors. So it's actually very important to see and probe this dephasing during the Latin spiral. By doing that, the LIGO collaboration has put some constraint on the pressure and density of using the event, the binary neutron star that was discovered. And also they could actually measure with a certain accuracy the radius of the neutron star. Now, besides the binary neutron stars, the LIGO collaboration has also detected mixed binary, a neutron star and a black hole. And this is the first robust detection that happened the 15th of January 2020. This is a simulation done by Tim Dietrich of the event. You see the neutron star going around, or the black hole and neutron star going around each other. And because of the parameters in the binary, the mass ratio and the spin of the black hole, there is no disk that is left around after the neutron star is swallowed by the black hole. So in this particular case, there was no way to produce an electromagnetic counterpart. And in fact, the only way one could conclude that this event had a neutron star was by looking at the reconstruction of the masses, which are here in blue. You can see that the masses of the secondary lies in the region where you can have basically neutron star. Between, let's say, 1 and 2.2 solar masses, while the other object had a larger mass, so we think it's a black hole. Now, the only event I can talk about of the ongoing run is actually the one discovered the 29th of May 2023 that I alluded at the beginning of my presentation. This has some peculiarity because the mass of the primary it's quite small for a black hole mass. So it's the smallest black hole that LIGO and Virgo have seen so far. In fact, it lies in this region that astrophysicists call the low mass gap, that we don't see black hole with this mass in our galaxy in X-ray binaries. And if you reconstruct the signals and infer the masses, this binary is somewhere here. This two-dimensional Gaussian distribution here. This was the event I was showing you before, which had this large asymmetry in the masses. This is GW170817, the first binary neutron star. There was also another binary neutron star discovered by LIGO and Virgo with no electromagnetic counterparts. And these are the two neutron star black holes that were observed. Okay, by the way, you are very welcome to ask questions, of course. Okay, so let me skip that part. So I want to say something about the tests of general relativity, which are done with these observations, which are unique to gravitational waves from binary system because we are probing space-time, dynamical space-time, and large velocities and strong field very differently from what we can do in our solar system. And I want to first discuss the test that is done once the two black holes merge with each other and they form a new black hole, and the black hole rings the space-time, producing quasi-normal modes. So this is what happened at the very end as I said, when the two black holes merge with each other. And you can do a kind of analogy. If you look at the electromagnetic spectral lines, they can identify chemical elements, as you know. In general relativity, the quasi-normal modes depends only on the mass and the spin, in particular for astrophysical black hole, the mass of the spin of the black hole. So if you can measure them, and in particular more than one, you can get information. You can know whether the black hole was the Kerr solution, or Schwarzschild solution that I alluded at the beginning of my presentation, or maybe a black hole in some theory which is not general relativity. So one way to do this test is that, so you consider, for example, your inspire merging down signals. You include a deviation from the quasi-normal mode frequency in general relativity, and then you allow this deviation to be free, and you change this together with all the parameters on which the waveform from the binary system depends on. And just to give you an idea, this is the variation in the waveform when you change the frequency. This deviation of 50% of it, you can see the variation in the waveform and in the frequency. If you change the decay time, you can also get a deformation of the waveform during the ring down. So this analysis is done by the LIGO-MIGO collaboration as part of the test of GR. And these are the results recently updated for all the events in gray, highlighted the two best events that allow for a measurement of this deviation in the ring down from the very first event and the one discovered the 29th of January 2020. The GR value is here, so the results encompass 0, which is good, so it means GR has passed the test. This is the bound that one has obtained putting together all the events. So these are the kind of errors that we have today. I want also to highlight that there are more agnostic also tests of the ring down that are done by the collaboration and also by other groups outside the collaboration, where you use a superposition of dumb sinusoid to basically describe the ring down signal without taking into account the rest of the signal, the inspire and the Planck one. And they also have obtained results not just for one mode, but even more than one mode, which is quite interesting. Now, I want to describe another event here, another test of general relativity. I'm looking at my time. I have 15 minutes, right?
15 more, yeah.
15 minutes more, okay. 20 minutes from my time, okay. So the other test that I wanted to describe, for people here familiar with the parameterized post-Newtonian test, which is done in the solar system, is something similar, but of course it concerns gravitational waves and the parameterized form of the phasing of the gravitational waves. So in the frequency domain, you have an amplitude and the phase can be expanded in post-Newtonian theory. You have a higher order correction in V, and the red coefficients here are the prediction from GR. And now, in the same way of the test of the ring down, one can add deviation parameters that then you can vary and you can determine during your Bayesian analysis. Okay, and this deviation from general relativity can be, as I said, varied with all the parameters on which the binary depends on, the waveform depends on, which are, I didn't say that, but for binary black hole, we have 15 parameters. The masses, the spin, and the orientation of the binary with respect to the detector, etc. So you do your Bayesian analysis and you marginalize on all the other parameters and you look at the posteriors for these deviation parameters. If they encompass 0, it means that the test, GR has passed the test, right? This happens, and then you can put a bound on this parameter delta psi. And these are the results for the different post-Newtonian parameters at Newtonian level 0.5, 1 pn, etc. I want to focus on -1 pn, which is the dipole emission. So the results here that you see are for different events in gray, and putting all the events together, you get the bound in red here. These are the previous values. Now, what I wanted you to focus on is that the dipole emission is the case in which you are not in general relativity, you have a scalar field, and so the leading radiation is not the quadrupole, but the dipole. Okay? And the best bound, not surprisingly, is obtained with a binary neutron star that was discovered because it had a very, very long inspiral, 3,000 cycles. And so during that inspiral, you can actually test the dipole radiation very well. And so this is at the level almost of 10 to the minus 5. The next best bound is the neutron star black hole that I was just describing before, which had a low mass, so was also a very long event. And the interest of this event, which the deviation is of the order of 10 to the minus 4, the bound, it's interesting because for the first time we are putting a bound on a black hole. You have a neutron star black hole there, not two neutron stars. And in fact, people have used this bound to actually apply it to some specific, modified theory of general relativity. Okay? So this is quite interesting. Now, let me move forward from this test. I want to come back to the modeling.
I'm sorry for
Yes.
the public. What does it mean, a fractional post-Newton order, post-Newtonian order, 0.5 or 1.5?
So basically means that with respect to the GR values, if you have a deviation from general relativity, it has to be smaller than this 10 to the minus 5 or 10 to the minus 4. So you cannot have
of 0.5 post-Newtonian.
sorry, you're actually 0.5, well, it's a correction here that it's V instead of V squared. So V squared is 1 pn, and in general relativity, you don't have a correction that goes like V. So this is actually not, sorry, maybe this is what you meant. At 0.5 is an absolute correction, is not a deviation, because you don't have the GR value. I don't know if you meant this.
Yes, because I expected 0, 1, 2. So
Yeah.
these are non-GR results.
Yeah, so this is an absolute value. It's not, a deviation with respect to the GR value will be just 0, so in an absolute value.
But 1.5, 2.5 is GR, right?
Yes, at
Just
1.5 v to the cube, which is 1.5, you have these tail effects that are due to the fact that the gravitational waves backscatter with a black hole before going, to infinity due to the nonlinearities. And you can have spin orbit coupling, the spin of the black holes, at this 1.5 per Newtonian order. But minus 1 pn is not there in general relativity. Okay, so I wanted to actually, So let me now discuss how we are progressing. So starting from the first observing run, we are now at the fourth observing run, and this number tells you the range at which we can see a binary neutron star. So if you see the number growing, means the detectors are becoming more and more sensitive. And in fact, today, the LIGO detectors reach 160, 168 during the fourth run, which is very nice, and Virgo around 60 megaparsec. And as I said at the beginning, we have 203 candidate signals during this run, which will end sometime in September, October of this year. Then there will be a gap for a few years to upgrade the interferometer and becoming, more sensitive, reaching between 240 and 325 megaparsec for binary neutron star, which is very nice. And they will be used until the end of this decade. There is a detector in India built with actually LIGO technology that should be operating in late 2020, beginning of 2030. There will be upgrades of LIGO and Virgo called A-Sharp and Virgo Next. But these detectors are still looking in our local universe, redshift of 1 and 2. But even with the current run, we are reaching a total of 300, maybe 350 events, which is already quite a lot. With O5, we will go to thousands of events in some years. And so we have to start looking also other effects in the waveform. And one important effect is eccentricity. So this is actually a flux emitted by two black holes going around each other, which are precessing and also eccentric. And you can see the waveform now, which has all these spikes. These spikes are emitted close to periapsis, when the two objects come very close to each other before going away again, because the orbit now is eccentric. and you have a lot of radiation that is emitted around them, so the waveform is going to be much more complicated. But why this is important? Because we expect, although the majority of the event is quasi-circular, so until now we have only observed and used actually quasi-circular orbit templates.
I'm not
Yes,
mapping this right. So the little clock was for the expanding image.
the little
but
clock
the-
here.
Yeah, that was telling the time for your expanding image, I guess. And this line below is also a timeline, right? In terms of the.
Okay, so this time that you see here is the actual time that it takes from this point to merge with the masses that are here, which is 50 solar masses. Okay, the simulation starts earlier on, but the time is this one.
I
Of
see, you're
course, the
talking
simulation it
time
shows
front.
much more slowly, right?
Okay.
I mean, in order to see it.
Yeah.
Okay. Okay, so I was saying that this is important because we expect that the subpopulation of these black holes may come from other channels. For example, black holes binaries in globular clusters, which can be eccentric. In fact, in order to discriminate between channels, it's important to extract eccentricity, the precession of the spins, even the magnitude of the spin is important. So it's important actually to have this information, and there are many papers that have started to build this waveform with eccentricity. And I wanted to show you an example if you actually don't include eccentricity, okay? So if you have an eccentric binary, the binary is going to merge more quickly with respect to a quasi-circular because you have this strong radiation at the periapsis. But the fact that the binary merges more quickly, you can also obtain if you increase the mass of the binary. For a quasi-circular orbit, you also merge more quickly, okay? So what happens, you can do a study, you can inject an eccentric binary, you recover with a quasi-circular binary. This is an example for the next run of 5, and you completely miss, the true value. So the true value was eccentric at this shear mass. This is the mass ratio. The Poisson distribution is completely off from the true value. And even more importantly, the primary mass, which in this particular example was lying actually in the lower edge of the high mass gap, this region of 45, 60 solar masses where you should not have black holes, come from the collapse of star, you get a Poisson distribution if you recover with a quasi-circular template model that will give you a value of 90%, which is completely away from the true value. So this is just an example, it's an extreme example, but it tells you that you really have to include this effect, otherwise you misinterpret actually your system. And in fact, recently we have developed a waveform model with aligned spin, not the full thing, not still precessing. And we have used a machine learning code called Dingo that we developed with our colleagues on the Max Planck for Intelligence System. We have reanalyzed all the events of LIGO and Virgo, actually population 57 out of the 90 events. And we found, we compared the evidence of eccentric against quasi-circular, and we found that there are at least 3 events with a base factor larger than 10. But when, in particular, the largest, the more interesting event, it's a little bit not conclusive because there was a glitch that happened during actually the observation. And depending on how you actually remove the glitch, you can change the base factor by quite a lot. And I just remind you that a base factor larger than 27,000 is 5 sigma. So if you take into account the glitch, you actually can reduce this much lower than 5 sigma. So I don't think you can claim really that we observe an eccentric system. But I wanted also to emphasize that base factor is not the end of the story. You have to multiply the base factor by the prior odds from astrophysics. I mean, how likely you expect that the source was actually eccentric with respect to quasi-circular. And you expect maybe a few percent of the events to be actually quasi-circular. So at the end, the odds ratio is really, it's in this range. No? You can decide whatever you want. So I'm showing here the Poisson distribution for the eccentricity at 10 Hz for these 3 events. And the event I was highlighting here is this one. The Poisson distributions, the violin plot with higher modes or without higher modes don't change much. But the main point is that we cannot yet, conclude that we have observed an eccentric system, but it's likely that with this very large number of events that we are seeing, there will be a subpopulation that is eccentric. We have to be prepared to detect them. Okay, so now let me go in the last part to the future. Maybe I have 5 minutes. Yeah. Okay, so we would like very much to have new facilities on the ground. This is not yet settled. I mean, it's not funded yet, but there is a lot of work that people are doing. Einstein telescope in Europe that might be underground, and Cosmic Explorer in the US. So these detectors are going to improve the sensitivity with respect to advanced light by 1 or 2 orders of magnitude. This is the noise spectral density. And you can see also the improvement at low frequency. Now, if you improve at low frequency going up to few hertz, you can bring in band much larger black holes, right? I was telling you before, you have this cut due to the bandwidth of the detectors. If you go to smaller frequency, you can have thousands of solar mass black holes that you could observe. And these are in this region here. And because you improve the sensitivity, you can go also to much larger redshift. So you can go up to the time where the first stars formed, or even more than that. Now, what is overwhelming is the number of events, okay? So I was telling you with the next run, which is called 05, maybe we detect thousands of events, few thousands of events after 3-4 years. With Einstein telescope and Cosmic Explorer, in 1 year, you could observe 10,000 events, only with signal to noise ratio larger than 100. Of course, you have also the one with signal to noise ratio smaller than 100. This is 1 order of magnitude more than in signal to noise ratio the events we observe today. And of the order of 500 events for binary neutron stars in 1 year, with also large signal to noise ratio. Now, because you are bringing in band also this 1,000 solar mass object, you can also, if they exist, detect intermediate mass ratio in spiral with a mass ratio around 10 to the 3. And they are much more complicated. These are 2 snapshots at 1 Hz and 10 Hz, which is really much more complicated to model. Moreover, we actually, this is really going to happen. LISA, it's this beautiful experiment in space that has been adopted, is now under construction by the European Space Agency with large participation also from NASA, was adopted last year. It's an interferometer, an equilateral interferometer going around the sun and behind the Earth that should be launched in 2035. And this is opening a completely new bandwidth around the milliarth. This is the noise spectral density of the detector. And there are many signals here. So there are the massive black holes of million solar masses at the center of galaxy forming binary system and merging with each other with very large signal to noise ratio up to thousands. So even 2 orders of magnitude more than what we have today. And these are just the signal, the sweeping band that you can see here. There are multi-band binary black holes of 30-40 solar masses that start to be seen in LISA and then go out of band and then enter the bandwidth of the detectors on the ground after a few months or even a year. Okay, that's very exciting. There will be extreme mass ratio in spirals that I introduced some time ago. A small black hole going around large black holes. This, you see here some tracks of the different harmonics. And white dwarf in our galaxy. There are thousands, tens of thousands of them. Some of them could be seen also individually. Some of them create a confusion noise or stochastic background. Now, this is also a very complicated problem because this is not transient gravitational waves. These signals, some of them are always there for all the duration of the mission, which will be 4 or 5 years. So they are not just sweeping and then disappearing. The massive black holes could last for weeks or even months. The M-rays could last for the entire duration of the mission. So the data analysis is much more complicated than what we do today. I want to highlight 2 challenges. If you were using the waveform model that we have today, you can ruin some of the science cases, and I want to show you just 2 of them. This one is for ground-based detector like Cosmic Explorer or Einstein telescope. Sometimes they are called XG. So let's take a binary with a mass ratio 6, highly precessing, and let's put it at a distance like one of the events that we have detected today. But because these detectors are going to be more sensitive, O5 and A sharp, the signal to noise ratio is much larger. So one case is, science case is the Hubble-Lemaitre parameter, the expansion rate of the universe. You can detect it from gravitational waves because you can extract the distance to the source. And if you can localize very well the binary black hole, you can actually get the flow velocity and then the luminosity, and then you get the Hubble-Lemaitre parameter. So in this example, a signal was injected from one of our state-of-the-art templates, and it was recovered with another one from another family. One is the phenomenological, one the 31 body. The true values here, depending on whether you are looking at the system with O5, A sharp, or Einstein Cosmic Explorer, you get posterior distribution for the luminosity distance which are away from the true value more than 90%. And the localization in the sky is also off. This was where the event, the galaxy was, close to this galaxy was the event, and you can see that it's completely off. So basically you will get, due to the systematics, the wrong, this is not going to help the current tension that we have, certainly it's going to actually complicate more, so we have to get this right, okay? The other example is about LISA, the spectroscopy, these quasi-normal modes. So here we did an analysis where we injected a numerical relativity waveform with LISA with a signal to noise ratio around 200, and we recover, we do this test I was explaining before with the state-of-the-art waveform model that we have, and we got actually the wrong deviation parameter away from the GR value at more than 90%. So basically we will have a false deviation from general relativity due to the fact that we don't have all the physics, all the accuracy in our waveform model. And this, of course, we don't want to do that, right? Because this will be not really what we want. So we need to improve our waveform models by 2 orders of magnitude, which is not trivial, not trivial. I mean, in the last 10 years, maybe we have improved this waveform by 1 order of magnitude. We have to improve the waveform also for binary neutron star black holes. And we have to include all physical effects, as I was mentioning before, generic orbits, environmental effects. The binary could be in accretion disk. There could be a perturber, some other bodies that perturb, the dynamics. And I mentioned at the beginning that you should not worry about effect due to the propagation of the gravitational waves from the source to the Earth. But actually, these effects are important. They might affect 1% of the population. So in fact, people are already trying to take them into account. This is gravitational lensing. So if you have a waveform that is produced and passed through a lens with these different masses here, the unlensed signal, which is in black, can be modified with the colors here, depending on the mass of the lens. So you can have even like kind of echoes or multiple signals emitted from the same source due to the gravitational lensing. These are similar to the multiple images that you have from the same phenomena in electromagnetic astronomy, right? But for the gravitational waves, this means that you see a signal, and after a few hours or a week, you see another signal, but they were coming from the same source, okay? That's the effect. So how we want to do that? Well, first of all, you have to push this perturbative calculation, post-Newtonian, post-Minkowskian, gravitational force at higher order. You have to combine, or maybe develop even a new resummation scheme with respect to the 31 body. You need to calibrate much better to numerical relativity. And there is a lot of work that is going on from people in high energy physics that in the last few years have decided to help our community and applying their methods they developed for collider, physics to the classical two-body problem in this post-Minkowskian approximation. New results in post-Newtonian theory have been very useful in the last few years again. So in this plot that shows the post-Newtonian terms going in this direction, and the post-Minkowskian in this direction, the frontier is to arrive to basically 6 post-Minkowskian and 5 post-Newtonian here. So we hope to do that in the next maybe 5-6 years, which will be very important. And the gravitational self-force problem. So this is the most complicated problem, is this small object going around the large black hole, producing, a waveform very complicated. You see here the trajectory of the small body going around the large body. And this can be solved in this gravitational self-force. And today, the state of the art is quasi-circular, non-spin. And we have to arrive to the full thing, eccentricity, and also spin precession. So we have more or less 10 years, even less, because you have to build the pipelines and they have to be ready for LISA. So I have one slide, but maybe I can skip it. Okay, I will show you.
Whatever you think's best. Probably we should try to wrap it up.
Yes, I just wanted to, maybe I can skip it. You can ask me, this is machine learning, how to improve, but I will skip it. So summing up. So until now, this solution of the 2D problem has been very complicated, but so far successful in the sense for all the events that we have discovered with LIGO and Virgo, we have not seen systematic. We think we are interpreting quite well the events. And this has been possible thanks also to this really work at the interface between numerical and analytical relativity, because you can, they have their best tools, and we have to put tools together, okay, to produce these waveforms. Now, this plot here is showing you what will happen in the future, right? In the future, the signal to noise ratio for an event like if we were detecting today, this event, we will be, around 100 in signal to noise ratio, maybe 50, okay? Originally, this event was 24, if I remember correctly. But going into the future with new runs, new facilities, we will see this event with 1-2 order of magnitude better sensitivity. The number of events is huge. I was telling you before, more than 10,000 with very large signal to noise ratio, and even more. And LISA, this is just an example for massive black hole that you can reach these very large values. So I was telling you, we need to improve the waveform by 2 order of magnitude. This is very complicated, but I think it's very important if we wanted to get the physics, correct physics out, or astrophysics, or cosmology. And so there is a lot of work and opportunities for people working in theoretical physics, I think, that you may be interested in joining. I want to thank my division. A lot of work I presented also is based on their work, and also the agency and the collaborations. Thank you for your attention.